Hello, welcome back. This is our video solution for problem 4 from the second quiz. In this problem, we're really just asked for a definition, right? So there's actually not a problem to solve. We want the definition of a continuity, right? So we want the continuity of this is a function of two variables at a point. So we just got to know what this means. Um, I'll say sort of what the standard definition is, and then we'll maybe expand upon it just a little bit. So first thing, continuity, right? This is in response to the fact that when we take a limit, right? So for example, if I take the limit as xy approaches a point AB of the function f of xy, uh, I'm not supposed to plug AB into the function, right? I just need to know what happens near the point AB. And continuity is saying, well, actually, it should coincide with what happens at the point AB, which of course first means that AB has to be in the domain. So for a function to be continuous at a point AB, you need, and this is how we usually write it, this limit to equal f of AB. All right, but it's probably worth pointing out that there's a lot of assumptions when we write down something like this. So what are the assumptions, right? So what does it really mean? So f is continuous at AB if, so first thing is, right, a comma b needs to be in the domain of f. So AB is in the domain of f. If it's not, you can't write down f of AB. Okay, so that's number one. Number two, this limit on the left has to exist, right? You actually, no matter which direction you approach AB, the limit of the values of the function f should be the same. So the limit as xy approaches AB of f of xy needs to exist, so must exist. And then once you know that AB is in the domain, so it makes sense to compute f of AB, and once you know that the limit exists, and then it makes sense to ask, well, if this limit exists and this value of the function exists, are they the same? So that's why we'll write this now third. So the limit as xy approaches AB of f is equal to f of AB. Okay, so that would be a reasonable definition. Now, I want to write down quickly an alternative version of this last equality that for those of you who are, for instance, going on in mathematics, might be a little more instructive going forward, even if it looks a little bit peculiar. So one of the things we can do is, well, I'm just going to copy the left-hand side here. On the right-hand side, instead of writing f of AB, I'm going to write f of the limit as xy approaches AB of x comma y. So, I mean, I think it should be reasonably clear that as xy approaches AB, the limit of the pair x comma y should be AB, right? So this should equal a comma b. No real question about that. Okay, and so the way you should interpret continuity from maybe more high level point of view is that a function is continuous at a point if the function commutes with this limit operator. So I can evaluate f and then take the limit, or I can take the limit and then evaluate f. It doesn't matter which order I do it, right? So if we were going to summarize this quickly, we'd be saying the limit composed with the function is equal to the function composed with the limit. Right? So this is in some sense what continuity is really trying to get at. Right? So another idea of continuity here. And you're going to find as you move up through advanced calculus that this notion of when can we commute a function with another operator, maybe a derivative or very often an integral, that's going to be one of the central questions that you're trying to study. All right. So for this class, of course, we need to know this left-hand side, but for moving forward in mathematics, it's pretty good to understand this right-hand side, and I hope that's been illuminating.